Hi guys. Well, the headline is, and the news flash for you today is that there is a very, very easy way to do expected value when you're dealing with conditional probability / Markov chainy kind of things, and you're expected to come up with an expected value, which usually involves tree diagrams and the whole messing around thing, and you know what I mean. So I'll show you something today which hopefully will really help you, okay? We're using an example here where we've got John, and John is an athlete. He performs in triathlon events, which is running, swimming and cycling. If he wins an event, then the probability that he will win the next event is 0.75 or 3/4. However, if he loses an event, the probability that he will lose the next event is 0.8 or 4/5, guys. Now, it happens that John has won a triathlon and he then competes in the next 3 events. So what is the expected number of wins from these next 3 events? Okay, take a moment to digest that, and then I'll show you the slow way and the quick way. Okay, now this is the slow way, the traditional tree diagram way. Abracadabra, there's your tree diagram. So we've got his first win here, then there's this first subsequent event, and then the second subsequent event, and then the third subsequent event, and there are all the outcomes. Let's put the probabilities in. You'll just have to believe me. I did do it correctly, I can assure you. Now, what do we do now, guys? We've got to get expected value out of all this. This is the slow road. We'll call X the number of wins, and then we'll label them with their respective discrete random variable number. That's 3 wins, 2 wins, 2 wins, 1 win, 2 wins, 1 win, 1 win, no wins, okay? Now, what are we going to do? We're going to work out their probabilities, okay? So you can just do these at your leisure. I'm just going to whiz through them. Pause the video and just check that you believe me at your leisure, okay? Now, once we've done that, we can now assemble our distribution, our probability distribution table, okay? So we'll go over the screen and we'll do that, okay? So from the above tree diagram, the probabilities that X is 0, 1, 2 or 3 are calculated by adding the individual probabilities of their occurrence, and these results are summarised as a probability distribution table as follows, right? Now, e.g., if you want to get the probability X is 0, there's only one occurrence, so that is going to be 1600ths. The probability that X is 1, I think there's 3 of those. I've colour-coded them, so these brownie ones, that one, and that one. You add up the respective probabilities for that one, and that one, and that is the cumulative probability for when X equals 1, and so on and so on. You get the idea, don't you? You've done this before, I know. Okay, now, there is our distribution table from which we can work out the expected value of X. Okay, so it's 0 times this, plus 1 times this, plus 2 times this, plus 3 times this, and it's very boring, and we get 1.899 to 3 decimal places. So that is the expected number of wins from the subsequent 3 triathlons after he won the first one, okay? Alright, so far so good. I probably haven't taught you anything new there. So, but having a look at this now, there is an alternative approach which is considerably faster and easier. Although it is not intuitive, and the reason it works needs further analysis, which I will give you. But I'll first do it to demonstrate it for you, okay? So let's go for this. This is the alternative approach. Be prepared to be amazed, okay? Now, I've made up a transition matrix of John's triathlon situation, okay? So this, you know what that is. This is, along here are the givens, or the previous events, and here are the next triathlon here. So win given a previous win is 3/4, and so on. You get that? Good. The initial state matrix, which I'll call S subscript 0, is just 1, 0, because we know that he won the first triathlon. Yes? Now, watch this. Now, the probability of success in the first event, guys, in the first subsequent event, is, well, first of all, we'll say, okay, S1 equals TS0, which means we get S1 is this and this. Now, that's the probability of a win. That's the probability of not a win. So we can say that the probability of winning the first event, subsequent event, is 3/4, yes? Now, we'll do that same procedure now for the second and third events. So, therefore, the probability of success in the second event, we know that S2 is T squared S0, which means that S2 is what comes out to be 49/80ths and 31/80ths. So therefore we can say the probability of success in event 2 would be 49/80ths, right? Oh, I know. Just hang on. I'll get to the end in a minute. Now, this is the third event now. Same procedure. S3 is T cubed times S0, and you get this. And when you do that, so you get 859 1600ths and 741 1600ths, which means that the probability of success in event 3 is 859 1600ths. Now, what am I supposed to do with all that, you're asking? Well, guys, feast your beady eyes upon this. Hence, the expected number of successes is equal to the probability of success in the first event plus the probability of success in the second event plus the probability of success in the third event. I know, strange, but it's true. And if you do that, guys, you'll get exactly the same result as we got doing it the long way, which I'm sure you will appreciate in an exam setting is an absolute godsend. Okay, it is. So what we can say is that as a general rule, the expected value of success or not success in this instance, where we had 3 subsequent events, was T times S0 plus T squared times S0 plus T cubed times S0. And yes, I'm not kidding you, that formula works. That formula works, and that's the formula that I wanted to show you. In general terms, for an n-component multi-stage conditional event kind of scenario, involving conditional probability with n transitions, guys, we know that the expected value of x or not x is equal to the same thing generalised right up to the nth transition up here, t to the n times s0. Okay, yes, that's true. That's how they work. Now, I know you're scratching your head. Don't worry, I'll reveal all in a moment. NB, yes, the initial state matrix S0 relates to probability, guys. Probability, all right? Not any other Markov-y funny things, you know, but it has to be probability. Now, why does this equation work? Yes, you might well ask. Well, it is difficult to explain at face value. Yes, it is difficult to explain at face value, but rigorous analysis does reveal that the process of obtaining the expected value using the tree diagram approach and the traditional way of working it out involves exactly the same mathematics as that. Exactly the same mathematics as that formulaic approach there, okay? The only difference is that the calculations, they both proceed to the same result, but by a different order of calculation steps. That's what it is. They amount to exactly the same thing. Exactly the same thing, but just by a different order of calculation steps. All right, Wolfman, prove it. Go on, prove it. All right, I'm going to. This is illustrated over. Right, so this is the analysis of why this alternative approach works, because it is not intuitive at all. I'm sure you'd agree. All right, so we've got rainy days now. If it rains on a particular day in October, which is the wettest month in Melbourne, Victoria, Australia, the probability that it will rain the next day is 0.75. However, if it is fine on one day, then the probability of the next day being fine is 0.8. Okay? All right, so Monday is rainy. So what is the expected number of rainy days from Tuesday to Thursday inclusive, e.g. the next 3 days after Monday? Okay? All right, so here's our transition matrix. In fact, they're the same numbers as we just used for John in the triathlon, except we're doing rainy days here, guys. So, same deal, same transition matrix, except it's rain given rain instead of win given win here. And we've got a transition matrix, the same thing as for the triathlon scenario, because it was raining on the Monday, just the same as John did win his first triathlon. Now, we're going to use the tree diagram approach to show all the possible outcomes here. Okay, so, oh my goodness, abracadabra for sure. So here it is. All right, so just have a look, take it all in. Rain, rain, rain. That's the first rainy day. That's day 1, day 2, day 3. And I've done all the tree diagram, hoo-ha, for you here. Yes, tedious, isn't it? Now, I've got a little bit of a table over here. I'm calling these, I'm going to label these. This can be outcome 1, this one here, this bit here, there. In other words, what I'd say there is rain, rain, not rain. This branch of the tree would be outcome 2. And so on and so on and so on, right down there up to outcome 8, right? Now, the X values for these are, same as we got for John and the triathlon. So it was 3, 2, 2, 1, 2, 1, 1, 0. And I've worked out the probabilities here just for the sake of being complete here, all right? Now, there's a lot of information there, but that's the tree diagram approach, which we would use to generate a probability distribution and then work out the expected value of number of rainy days from Tuesday to Thursday inclusive, all right? Now, over the screen. There it is, just as a recap, okay? Now, for the expected value calculation, guys, let's do that. Now, what I'm doing here is, I'm just going to get rid of that there. Now, I've got the possible values of x being the number of rainy days from Tuesday to Thursday inclusive, right? 0, 1, 2, or 3. Wait a minute, Tuesday, Wednesday, Thursday. That's right, of course, yes, sorry. And now, what I'm going to do here, I'm going to talk about the probability that x equals that particular value of x, and which outcomes relate to that. So therefore, no successes at all. That would be outcome 8, wouldn't it? Which would have this particular probability to use in our expected value calculations. Yes, you see that? So therefore, we've got outcome number 8 for no rainy days. Yes. Now, for one rainy day, we would have, okay, let's have a look. This would be outcome 7 or outcome 6 or outcome 4, wouldn't it? Yeah, 4, 6 or 7. You get the idea? I'm basically putting in that table which outcomes I'm talking about. And you would of course add up their respective probabilities, wouldn't you? To get the probability, the actual probability. But in this case, I'm just going to put the outcome numbers in here. You'll see what I'm doing in a moment. Now, for 2 rainy days, I can have outcomes 2, 3, or 5. Let's work that out. That's outcome 2, outcome 3, outcome 5. That's right, isn't it? And for 3 rainy days, I want outcome 1 only. Yes? Now, if we then work out x times its probability, what it would be 0, this value of x, 0 times the probability of outcome 8, wouldn't it? Yes, 0 times the probability of outcome 8. Now, for 1 rainy day, you would get 1 times the probability of these things combined, okay? Right? You get that? Do you see what I'm doing? Okay, well, just keep with me. You'll see in a moment how this all works out. Now, for 2 rainy days, you'd be multiplying the probabilities of 2 plus 3 plus 5 by 2, wouldn't you? Yes? Good. And for 3 rainy days, you'd be multiplying outcome 1 by 3. All right? Now, what does that come to, guys? It comes to, if you summarise all that, we're saying that the expected value of x is 3 times the probability of outcome 1 plus 2 times the probability of outcomes 2, 3 and 5 combined, plus probability of outcome 4, plus probability of outcome 6, plus probability of outcome 7. All right? Now, that's what you get for the expected value. All right? Yes? Good. You understand? All right, now, over the screen. That's where we got to. That's the recap. Okay, now, what we're going to do now is we're going to do it the alternative approach, and you're going to be amazed. Watch this. Now, firstly, the probability of day 1 being rainy, guys. Okay, the probability of day 1, and then the probability of day 2, and then the probability of day 3, and then add them all up. That's how you do it, remember? So, the probability of day 1 being rainy is 3/4. Is that right? 3/4. Yes, it is, isn't it? Because it's 3/4 rainy and 1/4 not rainy. Now, that 3/4, guys, if I was to take this to the end result for all these little branches out here, that 3/4 could be found by adding this one, this one, this one, and this one, because they're all part of that bit of the tree, which emanated from this one here at 3/4. Do you get that? In other words, this times this times this, plus this times this times this, plus this times this times this, plus this times this times this. In other words, the whole half of the tree will all come to 3/4. It'll all come to 3/4 because that's what it is. It's 3/4, all broken up into all those little branches and twigs. All right? So what it means is, basically, yes, from the tree diagram, this is equivalent to outcomes 1, 2, 3, and 4. In other words, this one, this one, this one, and this one all added up. That's what it is. All right? Right, that's what that is. Now, secondly, the probability of day 2 being rainy. Now, let's have a look at that. Now we're looking at day 2, which is here. That's this one or this one. So they've got to be added up. Now, similarly and equivalently, this one is equivalent to, broken up into its twigs, out here at this end of the tree. That one would be outcome 1, outcome 2 would come from here, and from this one, rainy bit, this would be from outcome 5 and outcome 6 combined. Do you see that? Yes, that's how you work it out mathematically, and it comes to, equivalent of outcomes 1, 2, 5, and 6 combined, which is 1 plus 2 plus 5 plus 6. All right? Now, how are you going? I'm just about running out of voice here. All right, now let's we'll go over the screen now, and we'll just finish this off with the probability of day 3 being rainy, and then we'll see what we end up with in the wash. All right, so here we go. Now, that's what we had. Now, let's go with day 3 now. The probability that day 3 will be rainy. Okay, let's go day 3. That's this one, or this one, or this one, or this one. That's 1, 3, 5, and 7. So it's the equivalent of outcomes 1, 3, 5, and 7 combined, which is that 1 plus 3 plus 5 plus 7. Now, if you add all those up, the probability of day 1 plus the probability of day 2 plus the probability of day 3 being rainy, you will get, and you summarise it, you will get that. You pause the video and have a go and do it yourself if you like, but that's what you get. Now, the amazing, gobsmackingly, awe-inspiringly incredible thing is that this one here we got from working out the traditional expected value way, and this one here we got from this funny, non-intuitive, a bit weirdo way, using the transition matrix, are actually identical. They're absolutely the same as each other. They're the same result. So it does give you the same result. It's just that it's calculated in a different sequence with a different order of calculation steps. But the alternative method captures exactly the same probabilities. When all added up into an expected value, they come to the same thing. Okay? Yes, and I think I'm a bit of a star for doing all that for you, and I hope that, of course, you are a star and you'll go far. And look, use that little bit of gold I just gave you in an assessment situation and save yourself some time. It's an absolute beauty. All right, well, thanks for coming and seeing me today. All the best to you, and we'll see you next time.